Okay, so we've done generalized z-squares, which is how we deal where we have basically this. We don't have the standard variance. So instead of the normal, the variance to the epsilons equals sigma squared r, we have the sigma squared v, and how do we deal with that? Which is good. Next thing we're going to do is say, well, how do we deal? Sometimes when you've probably seen this before, sometimes where you have violations of the basic assumptions, we've taken a log transform, or we may have squared the response variable. We've basically transformed the response variable to improve it. But that's a bit hard, because up until this point you probably tried a transformation, fit to your model, looked at your model, looked at your assumption, went, is it good or not? Tried another one. And often we told you which one to try. And the question is, can we automate this? And the nice thing about this is the story goes, there was two professors of statistics, Box and Cox, and they were chatting in the tea room one day and went, wouldn't it be really cool if we wrote a paper? Because it's Box and Cox, and that would be funny. So, what can we do? Oh, I've got this idea about transformations, let's do that. So they did it. Didn't think anything about it, it got published, that's it. Bit of fun. The problem is, it was really, really useful. Like, really, really useful. And like, everyone used it. And it's become one of the most highly cited papers in statistics. And it was all based on two people in a tea room having a bit of a joke. So let's actually think what this Box and Cox are doing. So, as I said, sometimes what we would do is we'd try a transformation, we'd look at it. Often because we're taking logs and that, we need a positive variable. We have a look, we find out the right one, and there we're good to go. Can we automate this? Well, this is what Box and Cox did. And it's a really nice thing is they said, let's think about a standard transformation that is parameterized by a single parameter lambda. So we're going to say that y transformed according to lambda is y to the lambda minus 1 over lambda, if lambda is not equal to 0, or log of y when lambda equals 0. And in fact, you can actually show that the limit as lambda goes to 0 of y to the lambda minus 1 over lambda is log y. So this whole function has a single parameter y, and it gives you a transformation. It's continuous. So you can choose it. You can go, well, if I want a square, lambda equals 2. If I want a log, lambda equals 0, etc. But the nice thing is you've got this transformation where you just sort of take your response variable, you put in lambda, and it spits out the values. So this is how we're going to do it. We're going to treat lambda as an unknown parameter. And we're going to estimate the best parameter to fit our data. So we're saying, it's almost like we're trying all these different transformations, but we're automating doing it so we can actually see the best one automatically. We call that lambda hat. Then once I've got my lambda hat, I now do that transformation. I use my transform data in my linear model. And then I have a look at my regression diagnostics. If they're good, great, lambda hat was the right one. If they're not, no sort of transformation is available. Let's try something else. And what we do is once we have that lambda hat, we sort of go, let's assume it's a constant. So we just put it in our model as if it's a constant thing, and then we go in the standard way. We could treat this lambda hat as a parameter estimate through the entire analysis taken, but Box and Cox, when they wrote the paper in 1964, that said, well, that's better, but the extra complication doesn't make it that much better, so don't bother. So how are we going to do this? Well, first of all, we could have our full log likelihood. So we're going to look at log likelihood. Remember, log likelihood is the log of the function that equates all your parameters, in this case your betas, your sigma squared, and now your lambda, to the data. If you don't remember log likelihood, go back to stats, model, and inference and just give it a recap. But what you can do is you can say, if I knew lambda, let's assume I sort of came along and said, oh, lambda's 4. It'd be easy to do that transformation and look at and get your maximum likely estimates of beta hat and sigma hat squared. And in fact, so we know it was for a given lambda, we will put the little subscript lambda there. So we're saying, if I knew lambda, I can get my beta hat and my sigma hat. So what we're going to do is we're going to have a thing called a profile likelihood. Your profile likelihood is the likelihood you would have if you substitute in those beta hat, lambda, and sigma. So you go, I fix lambda, and I'll shove in my maximum likely estimators. Now that function is a function of lambda. Now I'm going to take this profile likelihood, and I'm going to find the best lambda. So you go, for each lambda, I can work out the best likelihood I could get. Now, of all those likelihoods, I have a slice or profile for each individual lambda. work out which lambda gives you the best. In fact, you can work out confidence intervals. You can say these are the sort of confidence interval for my lambda, the ones that I think are best. And then we often choose a convenient. So if I found the best lambda was 0.01, I'd probably go, actually, let's set lambda to 0. Let's have a log transform. The other thing we need to do is, because we're going to have log transforms and these sort of things, we need all our response variables to be non-negative. In fact, we need them to be positive. So often what we will do is we will just add an extra value to it to make them all positive so we don't get it crashing. So you can show that the profile likelihood, the thing that we're going to maximize to get our lambda, is some constant, so we don't care about it, minus n over 2 log the residual sum of squares. And the residual sum of squares, remember, is your fitted minus your observed minus your fitted model. But it's for the model for a new variable called z lambda. And z lambda is your y lambda, so it's your transform y, divided by, okay, y dot lambda minus 1, okay. What do I mean by that? That is your geometric mean. You take each of your observations and you raise it to the power lambda minus 1, and you calculate the geometric mean. What's the geometric mean? If I have n of them, I multiply them all together, and then I take the nth root. That's what I mean by geometric. So arithmetic mean, add them all up, divide by how many. Geometric mean, multiply them all together, take the nth root. So where does this all come from? Well, let's think about it. First of all, we're going to say we've got our transform variable. So here's our I transform variable, and it's going to be normally distributed. But I could take its design matrix, because it's a linear combination of the predictors for the ith observation times the beta sigma. And I can quickly use the transformation rule to get my likelihood, or my PDF for that individual point. It's the standard normal. There you are. This extra bit is because I've transformed it. I've transformed it into the original, so this is now f of yi. So I've gone from my transformed I lambda across. So this is my Hessian. So now I can substitute this in, I can multiply a whole load of them. So here is my full log likelihood for this point. So all I've done is I've got my product there, I've got my yi lambda transform minus xi beta over sigma squared, all done. Oh, if I simplify this, what I get is I get this term here, which is constant. I've got minus n over 2 log sigma squared. I've got y hat lambda minus xi sigma plus this extra term here. And I can say, well, let's now maximize this to calculate what my beta, my maximum likely estimate of beta is, and my maximum likelihood of sigma squared. Well, the nice thing is this is just a linear regression, and that's a known thing. These terms here don't really count. And so you can find that your maximum likely estimators for your betas will be x transpose x to the minus 1, x transpose y lambda. And if we maximize our sigma squared, we get RSS of y hat. So basically, it's exactly the same as standard linear regression. It's just now, instead of y, I have y lambda. Okay. You might notice and go, well, shouldn't this be n minus p? No, no. The key thing is when I do maximum likelihood estimates, you don't get the standard degrees of freedom. It's just n, which is why you may have been told the maximum likelihood estimates of sigma squared are actually biased. This is the reason why. But now I'm going to take this beta hat, I'm going to take the sigma squared, I'm going to substitute it into this. So wherever I get a beta, wherever I get a sigma squared, I substitute in, I rearrange, and this is what gets popped out. And then I can just start dragging some of these things together. They're constants with respect to our lambda, so we don't care. And I end up with this n over 2 log RSSY lambda over this. Okay, almost there. It's looking like the thing that we want, this likelihood. And we just use the fact that if I have the residual sum of squares of some CW, I can bring the C out the front because it's squared C squared W. And so basically I can rearrange it and I get this profile likelihood, which is fine. I can take my Z, I can take my lambda, I can basically substitute that in, and then I can maximize that. And that's what we do. So there's all the theory that lies behind it. What we're going to do, we've already seen it once before. If you go back to one of the previous case studies, I can't remember off the top of my head which one it was. I actually quickly did the Box Cox thing. But what I'm going to do next is I'm going to look at some lung data, and we're going to find the right transformation to fit that data correctly. See you next time.